Hi everyone, and welcome back. In this lecture, we're going to move on from the functional approach that we've been using to create our plots so far, and move on to looking at the object-oriented approach that I've mentioned a few times now. With the object-oriented approach, instead of just calling functions like plt.bar or plt.scatter, for instance, we actually create figure and axes objects and then call methods on these objects to create our plots. And this method is often considered to be better than the functional approach, as it allows us a greater degree of control and flexibility over creating our plots, which is especially helpful for when we are creating complex plots or multiple plots within the same figure. Let's go ahead and move on over into Jupyter Notebook and get started. Okay, here I am again inside of the same notebook that we've been using throughout this section. The first thing that I'm going to do is go ahead and create two basic NumPy arrays. Our first one, which I'll call X, will just be made with linspace, which generates evenly spaced values. And I'll have these start at 0 and go up to 5, with 11 total values. Linspace is inclusive for both our start and stop values, so both 0 and 5 will be included in this array. And then I'll just create another variable called y, which will be equal to x to the power of 2. So, as mentioned, in this lecture, we're going to take a look at an object-oriented approach to Matplotlib, which will involve the use of canvas or figure objects. In Matplotlib, a figure is basically just a high-level container that houses all of our plots and elements. We create a figure object first, and then add plots and axes to this figure. So essentially, a figure is like a blank canvas that we can add our plots to. Let's go ahead and create a figure now. So I'll go ahead and say that figure is equal to plt.figure, and as this is a function, we'll need to open and close a set of parentheses. So now we've got a variable called figure, which contains a figure object, which we can see here. It has a default resolution of 640 by 480, and it currently has no axes. And also, if we call type on this, it'll return the matplotlib.figure object type. So now we've got this blank figure object, we can actually add some axes to it. In the same code cell, I'm going to go ahead and say axes is equal to figure.add_axes. And then inside of here, we actually need to add our axes, which we can do by passing in a list. This list will take 4 different values: the left, bottom, width, and height. And these values will determine the size of our axes, and they can range from 0 to 1. So basically, the percent of the figure object that you want to use up. And also, just to emphasize this here, it's important that we add in these values in the order mentioned before. So left, bottom, width, and height, as this is the order that the method expects. So let's go ahead and work through an example here. I'll pass in some numbers to our list. So I'll go for 0.1 for our left and bottom values, and then for our width and height, I'll just put in 0.9 for both. If we run this, we'll get a blank figure containing our plotted axes. So basically, we've created a new blank figure and then plotted a set of axes onto this figure by calling the addAxes method on it. The next thing that we'll do is actually plot on this set of axes, and this will be familiar to what we looked at before. I'll just say axes.plot, and then I'll pass in the x and y variables that we just created. And then if we run this, we'll get a line plot, but this time it's being plotted using an object-oriented approach with the use of figure objects. This way is a little more involved and does have a few more steps to it, but it does give us a lot more control over how our figure and data is plotted. Just to quickly recap this, we started off by creating a figure object and then assigned this to a variable called figure. Then we created a set of axes by calling the addAxes method on our figure, and then finally we plotted our data on that set of axes. And then we can also add labels to this, but instead of saying plt.xLabel for instance, we'll actually pass in the name of our axes object, which we set to axes. So axes.set_xLabel, and then we can pass in our labels here, as well as any formatting or styling if you wanted to. And then I'll just go through and do the same for the Y label and the title. Okay, perfect. Let's now go through and have a look at another example, but this time we'll actually add in two different plots, and then we'll add in a legend to help identify each of our different plots. So this is similar to what we looked at in the last lecture, but again this time we're doing it with an object-oriented approach. I'll start here by again creating a figure object with figure is equal to plt.figure, and then I'll create a new set of axes by saying that axes is equal to figure.addAxes. And then for our axes, I'll just use the same values that we did before, so 0.1 for our left and bottom, and then 0.9 for our width and height. So far, this has been the exact same process as what we just did. So we've created a figure object and then created a set of axes. And then I'll also add in some labels and the title to this. So X label, and then our Y label, and then I'll finally add a title in as well. So with this all done, I'll go ahead and actually create our first plot here, which will be with X and Y. And at the end, I'll also add in a label argument, which, as we looked at last time, we need for our legend. So I'll just set this to be X, Y, but then I'll actually add in another plot as well, which I'll have as Y and X. And again, I'll add in a label for this one too. If we run this, we'll get our two plots, and then to add in our legend, we can just call legend again, but instead of calling plt.legend like we did last time, we'll call the name of our axes, so axes and then .legend, and then I'll leave the lock or LOC at default and let Matplotlib decide where to place it. So that is how you can put two different plots on the same figure object, which is similar to what we looked at in the last lecture, but just with a few differences in creating our figure and axes objects. The other thing that we'll look at in this lecture are subplots. These are a convenient way to put multiple different plots onto a single figure object without having to worry about creating and sizing our different axes. To create a subplot, we'll need to start by creating both our figure and axes at the same time. Let's go ahead here and say fig, axes, and then instead of saying that this is equal to plt.figure like we did before, we'll say plt.subplots. Running this will create a figure and axes object for us automatically, without us needing to specify the left, bottom, width, and height like we did before. We could just plot on this exactly the same as before with axes.plot and then our two variables. But let's say that we actually wanted to create 3 plots on our figure object. Inside of our subplots function, we can pass in how many rows and columns we want with the n rows and n columns arguments. We'll say that our number of rows, or n rows, will be equal to 1, and then our number of columns will be 3. And if we run this now, we'll actually get 3 different subplots within our figure object, with 1 row and 3 columns. It's possible to access these different plots by indexing. So if we wanted to plot some data on our third plot here, we could index it by saying our axes object and then indexing it at the second position, which again, as this is 0 based, will select the third element. If we plot x and y on this, only this subplot will get used. And then if we wanted to, we could plot different data on our first subplot. So for instance, here we could plot y and x. So our first and third subplots are plotting different data. It's also possible to access the individual titles and labels for each of our subplots too, like this, which really gives us a lot of control on what data we plot, but also massively simplifies the process of creating them, as we don't need to specify or worry about creating our axes. And Matplotlib just sorts all of this out behind the scenes. Also, as we looked at in the last lecture, calling plt.typeLayout on this can help with the appearance sometimes as well, just by adding in a little space between each subplot. Just to finish this lecture off, we'll have a look at some additional Matplotlib functionality that didn't really fit into any other lectures. So this will include things like changing the figure size and the DPI of our plots, as well as how to save them to a local file on our PC. I'll go ahead and copy down the code for our subplot from above, but then before running it, I'll add in the fig size argument to our subplots function. We can pass a tuple into this argument, which will allow us to specify the width and height of our figure in inches. The default size for this is 6.4 for the width and 4.8 for the height, which again, these values are in inches. I'd like to make this plot a little larger, so I'll set the width to be 10 and then the height to be 6. And then now, when we run this, we can see that our figure is quite a bit larger and all of our plots have been scaled up too. And then to increase the quality or change the resolution of our plot, we can specify the DPI argument, which is just the dots per inch, and this will change the resolution of the image. A higher DPI will result in a higher quality and sharper image, but also a larger file size. And by default, this argument has a value of 100. Finally, to save this plot to a file on our PC, we can just say fig, which is the figure object that we set here, and then call the save fig method. In parentheses, we can pass in what we want to call our file. So I'll just call this first figure and then .png for the extension. And this will then save the plot as a PNG file on your local PC inside of whatever folder your notebook is currently in. My current notebook file is within the section folder, so if I open that up, I can see that I've got a PNG file with the name that I just set, and then if we open it up, we can see that the plot has been saved to a PNG file but now on our local machine. And by the way, my plot is okay here, but if your image doesn't contain your plot title or is missing some axes, we can go back to our savefig method and pass in bbox_inches and set this to be tight. And this basically makes the content of our figure fit a little more tightly by removing any unnecessary white space around the plot. Okay, and that there wraps up our lecture on how to create figures and subplots within Matplotlib as part of an object-oriented approach. And then to finish off, we also had a quick look at how to adjust the figure size, DPI, and how to save a plot to a PNG file on our local PC. In the next lecture, we'll have a look at the practice activities for this section, which again will be a great opportunity to consolidate your learning from this section, as well as identify any areas that you might want to go back and have another quick look at. Again, any questions you might have, post them down in the Q&A section below, and I'll get back to you. Thanks everyone, and I'll see you all in the next lecture.